Broadcast is now starting. All attendees are in listen-only mode.
So welcome everybody to the PEI Masterclass series. We're excited about this first one in our series that we're getting started with Polar Educators International. Many of you are familiar with our mission statement that we're a vibrant network promoting polar education and research to a global community. We have two fantastic partners through ARCUS and CLIC. ARCUS has provided us with a secretariat and CLIC with the ability to have these webinars, so we appreciate their support. This first masterclass is titled Slip Sliding Away, Ice Shelf Collapse and Sea Level Rise. Most of you, I think, are familiar now with our new polareducator.org website, and if you haven't gone yet, please do. We're excited about how it's growing and evolving. There's a members area right here that you should have signed into to take part in the discussion portion of this forum. You can learn a lot more about Polar Educators by going to our webpage. Our vision statement is this. And one of the ways that PEI is working to meet the goals of our vision statement is to sponsor masterclasses like this one, focused on the needs of a dual audience, both educators and researchers. We're excited to present our first masterclass tonight, or this morning, depending on which time zone you're in. At the end of each of our presenters' presentations, you'll have an opportunity to pose questions. So you should see a question bar in your control panel, and you can type in your questions at any point during the presentation, and some of those will be posed at the end of each presentation. The other questions will be answered in the discussion group, which will begin officially on May 12th and run through May 23rd. So it is my great pleasure this evening to introduce Dr. Richard Alley, our first speaker. Dr. Alley is an Evan Pugh professor in the Department of Geosciences at Penn State University. He has demonstrated excellence not only in science research, but also in education, outreach, teaching, and service. Among his many awards, in 2007, he shared the Nobel Prize for his work with the UN Intergovernmental Panel on Climate Change. So, Richard, I'm going to switch screens here real quick.
Excellent. Thank you.
And hang on one second. Okay. And
I've been made the presenter. Show my screen. Yes, please.
Okay, so I'm going to turn it over to you. Yes, we are seeing it now on the screen. So it's with great pleasure that I welcome you, Richard. Thank you so much for being here this evening.
Oh, it is my pleasure. So if anything is unclear, please stop me. I hope that people will be able to see my screen here, and I'll be able to wiggle at you. So you'll see a great big iceberg there that I took a picture of in Greenland. And now I hope that we will go wandering forward here, and you will see, and my slides are not advancing. There we go. And thanks to you, and there's a big penguin. So we'll get you some more penguin pictures before we're done. So with that, I want to start the story here. This is, if I can
Muted.
This is a plot that shows CO2 levels at various times in the past, and it shows sea level relative to today at 0, with higher sea level flooding the coasts and lower sea level when ice was formed. And if we take this plot and we do the most naive thing possible, which is we connect the dots from these different times in the past, we take the modern CO2, not where we're going, but where we already are, run it down to the line, and run it across to the sea level that corresponded to this in the past, and then ask where 10% of humanity lives. This is not a prediction or a projection, but it is certainly a reason why you would be interested in ice sheets. Because if we get to a steady state with our modern CO2, it seems to be a level that would flood a whole lot of people. And we might run CO2 way off of this plot altogether if we go to a burn it all future. This is not just a correlation, this is causation. The CO2 made it warm, the warmth melted the ice with rather high confidence. So there's a reason to study this. This is a very US centric plot. For some reason, people like this one. If you put 6 meters of sea level into the ocean, it runs up towards Washington, D.C. there, and everything in red would be underwater. The state of Delaware would be very, very unhappy if something like this happened. And 6 meters is not a worst case scenario. As we will see, there's more water than that out there that could be involved. So sea level rise could matter. We have some idea what happens when this much sea level rise happens rapidly. So just recently in the US, we had a large storm named Sandy. Sandy was only, the highest storm surge was only about 4 meters. Most of it was only about 2 meters. But you will notice in these pictures shown here that, you know, what had been a bridge that you could drive on, just a small number of meters with a lot of waves did bad things. And if you notice the houses along here and the houses that aren't there anymore, sea level rise can be very big deal if it comes at you like that. Okay, sea level is rising. This is 1992. Oops, I apologize for that. This is 1992 on your left over here, and it runs up almost to modern in these data from the University of Colorado. There are wiggles that are related to water going onto land and coming off the land with rain associated with El Niños and La Niñas. But if you take those out, sea level has been rising at just over 3 millimeters a year, fairly steadily and predictably. I spent a lot of time dealing with people who said, oh, sea level rise stopped. Why don't you scientists quit lying to us? Those people were very quiet when it came back. But, you know, sea level is rising very, very clearly. Okay. Now, if you take that and you run it through the IPCC process, you give it to economists, they say it matters. You should deal with it, but it's not a big deal. And they say that partially because they are using an estimate which is fairly slow and small sea level rise. And they assume, typically, that society will make a highly efficient response to this knowledge. We will use this knowledge in the best possible way. So, for example, suppose that you own a beach house. It is a beautiful beach house. It sits on the beach. You have a wonderful view, and you can sit on your veranda and sip drinks and watch the waves come in. But the ocean is rising. You see the ocean coming, and so you quit maintaining your beach house. You quit fixing things. When the ocean finally takes your beach house, it wasn't worth much because you were not maintaining it. Now, I happen to own the land behind yours, and when you're gone, suddenly that beautiful view that you used to have, I now have. There's no loss, there's still a view. And so what happened? One old house was lost. Many of the economic estimates are very small for the cost of sea level rise. And for the U.S., I have seen projections that the entire United States coast, for 100 years, the cost of sea level rise will be less than the damage that was caused by one hurricane in New Orleans. Even so, the economists say that you should be investing money to slow down sea level rise by reducing fossil fuel emissions. But they say you shouldn't do a big amount of change on that because the cost of sea level rise will be low, because sea level rise will be slow, small, and expected, and you will respond economically. Now, I can tell you without necessarily blaming Katrina on global warming, but I spent 20 years before the hurricane destroyed New Orleans teaching students that the hurricane was going to destroy New Orleans. We had lots of studies, many of them had been made for government officials, that said that the city of New Orleans was sinking. The ocean was rising. The delta that blocked the waves was eroding, and the storms might be getting stronger. And if you have a lower city and a higher sea with less protection, that matters to how high you should build your levees. Every person involved knew the science of this with very high confidence for years and indeed decades before the hurricane hit New Orleans. So if we humans are efficient people and we do the economically efficient thing, then it is obvious that we actually raised the levees and there was no flood. But here's a picture of the flood. So when you find economists saying, well, sea level rise won't hurt us because we will deal with it, remember that they assume that this did not happen. Okay. So that's worth lodging in the back of your brain as we roll forward. Okay. But in addition, there is a question. They are making economic models assuming that the sea level rise will be fairly slow and small, and we'll see it coming. That is really a statement about ice sheets. The ocean is warming. Warmer water takes up more space. That raises sea level. But it's not a lot. It's something like less than a half a meter per degree C. Mountain glaciers are melting. That takes water out of the mountains and puts it into the ocean. But by the time we're a third of a meter or so, there aren't any mountain glaciers left. We take a little water out of the ground and let it run down the rivers to the ocean, but we build some dams that traps water behind them. Not much change. The real issue is that there are more than 60 meters of sea level locked up in the Greenland and Antarctic ice sheets. So the question, will sea level rise be slow and small, is a question, what will Greenland and Antarctica do? All right. Now, this is a plot that starts over here on in the year 2000, and it goes up to the year 2100 across the bottom. And it has various estimates of sea level rise. This thing over here that I'm pointing at now is sort of what the IPCC said in 2007 for thermal expansion and mountain glacier melting. The new IPCC numbers are a little bit above that. But on here are a whole bunch of other estimates, scalings against temperature, expert elicitations, and other sorts of things. I will make a point here. One of the grand old men in the field gave this estimate, this little low one. One of the grand old men in the field gave this estimate, which may tell you something about grand old men in the field. But in between, there are a whole lot of other estimates, and what you'll see is that most of them tend to track near or above the high end of the IPCC numbers. The IPCC has proven to be very effective and accurate in projecting temperature change. The IPCC in the past has underestimated sea level change. And if these other estimates are accurate, that might possibly still be going on. At any rate, this is still estimating a sea level rise. It's estimating that sea level rise will accelerate, and the uncertainties you will see are mostly on the high side. There is some estimate sea level rise could be a little less, a little more, or a lot more. That will come back. Okay, ice sheets have been contributing to sea level rise. 0.6 millimeters per year average since 1992. That is a huge amount of water, but at that rate, it would take more than 100,000 years for the ice sheets to disappear. I have a note down here that you might possibly see that the equivalent of 0.6 millimeters per year out of 60 meters of ice, The equivalent to that for me as a human being is if I went on a diet and I lost 1/3 of the weight of a single potato chip or crisp in a year. Now, it's very clear that I could lose weight faster than that. It is very clear that ice sheets have lost weight faster than that in the past, and we are driving temperatures up rapidly. And so the really interesting question is, will the ice sheets go on a serious diet? And so that's what we're going to talk about today. I'm going to walk you through the physics of this issue and see if we can answer that question. Okay, so we'll start with the physics. If you happen to be sitting there with a cup of coffee and you poured the cup of coffee on a table to make a pile, it will spread under its own weight. You will get a very wide, thin pile. If you have thick cream and you pour it on the table, it will also spread under its own weight, but it won't spread as far. All piles tend to spread under their own weight. If they're really strong, they resist it. So the building you're sitting in is not falling down. But the Gothic cathedrals of the past actually had all sorts of troubles because they did spread under their own weight, and the walls tended to bulge out and the roofs tended to fall in. And they had to devise flying buttresses to keep the Gothic cathedrals up. So strong things can resist spreading. If you push back, as with a flying buttress, that resists spreading. And if you made your table rougher or less slippery, that also resists spreading. And so you have a little thing up in here in the middle that you spread more easily on a smooth, slippery table than on a rough, bumpy one. Okay, essentially that is all the physics that we're going to need to talk about sea level rise, fascinating as it may seem. Okay, now I have here a picture of an Antarctic tern, and this is a bad pun. When I show you the picture of the tern, I am turning away for a moment from the story of the Antarctic ice sheet and saying a word about communicating. I have had the wonderful opportunity to talk to U.S. senators and representatives. Actually, I talked to a senator from France at one point, and I have gotten to talk to government persons. And so this is a little bit about how you might communicate to a government person if you meet them, or to your students. And one of the things which I think is really, really important, we do physics with equations. Things like the spreading stress on the ice is this. We can always turn the physics into real words, and we can do that accurately. It may not always be easy, but we can always do it. And it turns out that the statement, the pile is spreading under its own weight, and the statement, tau b equals rho gh alpha, are the same statement. And so one of the things we have to do when we communicate to our senators is find the way to turn our equations into things that make sense. For a pile, the weight of the pile raises the pressure inside compared to a point outside of the pile. That difference in pressure causes spreading. And it's fairly straightforward physics, and that's measured by this equation here, which you don't need. The key thing is we can put physics into English, or any other language you prefer. So at any rate, why with this pile thing, what is an ice sheet? It is a 2-mile thick, 3-kilometer thick, 1 continent wide pile. Snow falls faster than it goes away, and it builds up, and it makes this giant pile of snow. It gets squeezed to ice under its own weight, and then it spreads under its own weight. Snow falls on top, it spreads, and out at the edges, it either melts or it breaks off to make icebergs. If you turn up snowfall, it grows the pile, and because the water comes out of the ocean, that lowers the ocean. If you turn up melting, that shrinks the pile, and it puts water back in the ocean to raise it. If you increase spreading, it takes the ice down to make icebergs and float in the ocean, and that raises sea level. And the interesting thing is what controls the spreading. Now, the strength of ice doesn't change very much. It's not like changing from cream to water or water to cream. But ice does have a change in how lubricated the bottom is, and it has a change in the flying buttresses, how much it's held in. And so what we're going to do here is walk through a little discussion of changing how slippery the bed is under the ice. And then we'll do more discussion of how the ice is held in by flying buttresses at the edges. And that will get us through the physics. Okay, so if you go to Greenland in a plane and you fly over the west coast up on the ice sheet, at some point you will see these big lakes like this one that I'm squiggling on. The ice flows over bumps in the bed, and it makes hollows in the surface. The ice melts on top, and that makes giant lakes. And these lakes are kilometers across, miles across, and they can be 10 meters or more deep in the middle, 30 feet. And they're sitting on top of moving ice, which sometimes gets crevasses. And what happens if you have water that gets in a crevasse? It wedges it open. So a former student from Penn State who worked with me, Sarah Doss, and her colleague Ian Jochen went up and they studied some of these lakes. They floated around on one just like this one in their boat. Fortunately, they were not in their boat on the lake when the crevasse broke. Sarah here is standing in the middle of the lake after the crevasse broke. And you will notice there is no lake here. The lake has gone to the bottom of Greenland down the crevasse. And these are big crevasses. When this was happening, the waterfall was twice the flow of Niagara Falls in the US and Canada. It was an immense outpouring of water that went to the bottom of the ice sheet and made it, for a little while, more slippery. And so here is a cross section. At the top up here is air. In the middle is ice. At the bottom is rock. These lakes form on the ice sheet, and then they break through to the bed. And when they do that, they make it a little more slippery, but they also make sure it's not frozen, because that much water flowing turbulently through melts it. As the world warms up in the future, there are places that could have lakes that do not yet have them. And we believe that the bed is actually frozen at the bottom, that it's below freezing and the ice is stuck to it. If those places get lakes and those lakes drain to the bottom, that will thaw and that will let it slide faster, and that will take more ice down to the ocean, and that will raise the ocean while lowering the ice. It won't be instantaneous. The ice sheet will not fall in the ocean, but it will make Greenland more vulnerable to melting than it is now. In addition, this is a lesson that we're going to come back to, because when this happens, it's sitting on big bumpy bedrock, but as you're going to see in a little bit, that's not always the case. Okay? So now we're going to sort of look at Antarctica and a little Greenland. On your right at the bottom is a sketch of an ice sheet that my dear wife did. Air is above with the airplane. Water is down here with the boat and the fish and the iceberg. And what we're showing is that as the ice flows down to the sea, in colder places, when it gets to the sea, it does not immediately make an iceberg. It remains attached, but it flows over the ocean. This is called an ice shelf. It very often runs aground on a local high spot in the bed, and it usually sits in a bay, and it has drag from the rocky sides of the fjord or the bay on the side. The friction from this pushes back against the ice, and that keeps the pile back here bigger than it would be, in the same way that a flying buttress pushes back against the Gothic cathedral and keeps the sides from bulging out and the roof from caving in. Up here it is -50. It is not going to melt in the near future. This is at the melting point. This is close to the melting point. It can melt very easily. And this is where we're going to really concentrate, is if you lose this, you lose the friction, it lets the pile spread faster. That matters. Okay? Just to turn aside for communications for a moment, this is an accurate statement that ice shelves do for ice sheets what flying buttresses do for Gothic Cathedral. And by having the good fortune of having my wife draw a diagram of an ice sheet that looks like the Gothic Cathedral, I hope that it's evident what's going on here and that this makes it clearer. Okay. So at any rate, let me show you that Antarctica is warming. I could show you the data. The data are clear, but I'm going to show it to you with a couple of examples. This is a penguin picture I took a little over a year ago in South Georgia. Here are a bunch of penguins. These penguins are trying to cool off by putting their feet in the water. They can't sweat. These are lots of penguins trying to cool off by putting their feet in the water. And they are doing this because it's warm. Those penguins were down there you can see little tiny penguins down where I'm squiggling my pen around here, like these. The glacier ended down here in 1980. Now it ends here and it's retreating rapidly. And this is over a kilometer. It's about a mile in between. Warming has been happening. The ice is retreating. Okay, this is a chinstrap penguin. We're now down on Elephant Island. That's where Shackleton left his men when he sailed the open boat across to South Georgia to get help. This is an Adelie penguin on Elephant Island. These are chinstrap penguins on Elephant Island. And this is not where Shackleton left his men. They were a couple of points over, but it's very close to where Shackleton left his men in 1916. But when he left them, the glacier was depositing this lateral moraine and this till. And in fact, when Shackleton was there was a glacier like that. It's now out of the picture, but it was up there 100 years ago. And so all around parts of the Antarctic, we see this melting. We see the effects of warming happening. Okay. And just as an aside, any good geologist would have not needed the diagram of the glacier, but be honest, most people, it's nice to put it in. I hope it's helpful to you. We keep trying. Okay. At any rate, now this one is a very important story, and I'm going to get my squiggler in here. If you look down in the lower right, those previous pictures we were looking at were here off of the Antarctic Peninsula. That's where the down Elephant Island and up to South Georgia is just out of the picture and not really in here, but it was down in this area. We're going to look at the end of this red arrow at the Larsen Ice Shelf right down here. Okay, so on your left now, the big thing in black is the ocean as viewed from above. And on the left, this is the spine of the Antarctic Peninsula sticking up towards South America. It's a giant mountain range with glaciers dripping off of it. Icebergs you can see down in the ocean on the right. This is a scale bar over here, 12 miles or 20 kilometers. That's a big scale bar. So these are big icebergs. In between here is the Larsen B Ice Shelf. This is the flying buttress. It has friction with these islands up at the top. It has friction with islands down at the bottom. This ice shelf formed 10,000 years ago as the ice sheet got smaller at the end of the Ice Age. It sat there for 10,000 years up to January 31st, 2002. But in January 31st, there were lots of lakes forming on top of the ice shelf on the flying buttress. And you can see this sort of blue things that I'm drawing circles around. Those are lakes on top of the ice shelf. Now, remember what happened to the lake that Sarah Doss was studying. It got into a crevasse, it wedged the crevasse open, and it broke through to the bottom. There, the ice was sitting on a mountain range of Greenland, big, bumpy granite. Here, the ice is sitting on ocean water. What's underneath here is fish. And so now you're getting ready to break through this flying buttress from all of this melt that has started recently, and there's not much below. So I will make the labels go away, and then I will make the ice shelf go away. This took about 5 weeks. And you will notice it's a big change. Now, after this, this blue slushy up here, actually, you could paddle your kayak through that. That's little tiny bits of ice broken up. The friction is now lost with the sides, and as a consequence, this glacier at the head sped up 8 times, going 8 times faster than it did before. So this ice was already floating, but when it broke, it lost the friction. It's no longer a flying buttress. That lets the ice behind it go faster. The Gothic cathedral starts losing mass, and that raises sea level. Fortunately, there isn't much ice behind the Larsen B. But there are lots of other flying buttresses. And so while that was the Larsen B that went away, if one of these were to go away, there is much, 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 much more ice behind it. And so this is our concern, is that you can lose a flying buttress in a hurry. That can allow the pile to spread faster. In a hurry, that can raise sea level. Okay, this has happened in Greenland too. So we are looking, if you look first down at the lower left, there's a yellow arrow here, and you're in an airplane or a helicopter looking along this yellow arrow over here. This wonderful picture by Connie Steffen. The Greenland ice sheet is way up at the top of the picture flowing towards you. It gets down to the fjord, and these are actually icebergs sitting on top of ocean water in the middle with rock on either side. So it's rock over there, and these are icebergs on ocean water with the non-floating ice way up there. If you get in your helicopter and you fly along, headed towards this squiggle that I made, what do you see? A seal. There's ocean water under there, but not at the head of it. And in fact, we have colleagues who are instrumenting these seals with oceanographic instruments so that they can go dive and study the ocean for them, which is fascinating. Eventually, as you go past the seal would have been down here on the right. And this is a 100-meter, 300-foot high cliff sitting on top of something that is 10 times as high, sticking down to the bedrock way underneath. This is the Greenland ice sheet on the left, flowing along the arrow and coming down into the fjord where the seal was. Huge, thick ice, most of a mile thick, flowing very, very fast, making huge numbers of icebergs that fill that fjord. Okay? Now, if you were then in your airplane or your helicopter and you were the smiley face up here at the top, so this is you looking down, and what you're looking at is this square that I've drawn, what do you see is this. That giant 100-meter high cliff runs along here. The seal was down here. These are icebergs that broke off. There was an ice shelf, a floating buttress in this area. And in 1992, it stuck all the way out to here. And there was friction with the rock walls there. There was friction on the other side. And the ice was held back by that friction. Beginning right after 1992, the water warmed. The water warmed, it thinned the ice shelf, and then it broke off. And so the ice ended here in 2000, 2002, 2000. Now it ends way back up here someplace. It's retreated even farther. It was really fast moving ice here, but here it had almost tripled its speed. The friction was lost because of warming ocean water, which let the Gothic cathedral spread faster, which raised sea level. Okay, and this is contributing to it. And what did it was a 1-degree warming. So right out in front where you can get to the ocean water, when the flying buttress was happy, you had the blue curve. This is temperature in the ocean. Then it warmed 1 degree. And that 1-degree warming took out the flying buttress and almost tripled the flow speed of the ice, which contributes to sea level rise. So it happened in Antarctica, it happened in Greenland. All right? So now what are we going to do? Everything in color in this picture is below sea level at the bottom and can make icebergs. And we're going to zoom in on the one on the left there. And we're going to zoom in, everything in color can make icebergs. And we're going to zoom in on this little box on the left, because this is what's known as the weak underbelly of the West Antarctic ice sheet. This is what we're really worried about. Shown here in color is how fast the ice flows. The blues up in here are really slow. They're not going anywhere in a big hurry, and you can see the flow speed over here on the far right. That's slow values. The blacks are really, really fast. This ice is just screaming along. Lots of people have been studying Pine Island Glacier up here, but Pine Island is sort of like Jakobshafen. It's in a fairly narrow bedrock trough. Thwaites Glacier, shown here, going really fast, is a huge, wide ice flow that is sort of funneled into this narrow neck in the middle, but it's a very, very big, fast-moving thing. Thwaites is the most interesting glacier in the world because it is the one that is most capable of doing crazy things. Okay, now I'm going to take the ice away and let you see the rock underneath the ice. And that's done here. I've put in Pine Island Glacier is this black arrow, so this is Pine Island. These are that funneling of Thwaites Glacier that you see. The ice is way above sea level on top up here in the middle, but it goes into huge deep holes that go well over a mile, a couple kilometers below sea level. And so the ice comes out of these giant deep places that could dump amazing numbers of icebergs in a hurry, and it gets funneled up onto this bump, this ridge, in a very narrow place between mountains. So there's sort of a funnel here that's both vertical and horizontal, and the ice is stabilized on this bump. And past the bump, it goes into a hole and a wider hole and a deep hole, and oh my goodness. So let me take this and reorient it so it's easier to see. That's somewhat easier to see. And then give the analogy. If you've ever been caught in a traffic jam, you know that where lanes come together, where they funnel in, that you get a mess. And that if you could somehow stop that funneling, the traffic would flow more easily. Over here, if you could somehow get the ice to back up to where this is wider and deeper, it could dump icebergs faster. And then it could flow faster, and then sea level would rise and the ice sheet would go away. And our worry in a traffic jam, we like the idea of getting the funnel out of the way. For the ice sheet, we really don't. So that traffic jam really is a good analogy for what's going on. There is a funnel here, and if that funnel goes away, a lot of water comes up. Okay. You may possibly have seen there was a paper that came out this week looking at a different piece of Antarctica. This is over in East Antarctica, and it says if we raise sea level a little bit by melting a little of the ice there, at some point as we make it warmer, the funnel there will break, and then sea level will go up a lot. So this is not just Thwaites, it also applies to others, that you go a little bit, a little bit, a little bit, and too much warming, and bang, you lose the funnel, you lose the bump, and when that happens, really big things occur. Okay, so warming raises sea level, too much warming raises sea level a lot. Now, let me do a little model for you. This is something we did a few years ago, and it will show you what's going on with this funneling. It's the same story, too much warming, and things really change. So what I'm going to show you is a model that has water. It has some ice flowing from the left to the right and some air, and we're going to raise sea level and float it off the bottom. We could also do this by taking out the flying buttress. And I'm going to show you what happened to get to where it is now, and then what could happen in the future. Now, if the world were boring, completely, utterly, totally boring, so if there were no topography, no funnel, what happens is that as you push on an ice sheet, it retreats slowly, smoothly, and boringly. A flat bed, you know what's going to happen. You can see what's coming. Sea level rise is slow, small, and expected. The economists think the world looks like this. The real world looks like this. At some point in the past, the ice retreated from the ice age and it jumped to that funnel, that bump where it's now sitting. And it's sitting there, it's sitting there, it's sitting there, it's sitting there. And if you go too far, it goes somewhere else in a big hurry. And so let me compare to you sort of the economic world at the top with the real world at the bottom. And so we're now the real world at the bottom. We're sitting there, it's boring, it's boring, it's boring, it's boring, it's boring, it's boring, it's boring. Oh my gosh. This is a hard thing. Okay, so that's what we're really interested in. So when we look at the possibility of West Antarctic collapse, it's very clear from geologic history that it sat, it jumped, it sat, it jumped, it sat, it jumped. It's very clear that sometimes the ice sheet has gone away. There is modeling, and keep your eye tuned on the news over the coming weeks, but there is some modeling, some presented at AGU last year, that indicates that the collapse of West Antarctica might possibly already have started. But it's very clear that if it hasn't already started, it could, and that it could go really fast, much faster than what we're expecting once it gets started. Okay, so now let me rephrase this. You know that predicting something like that, it doesn't, nothing, woo, is really hard. And so this is sort of a risk management problem, and we deal with analogous things. So let me give you the analogy, right? If you possibly know, I get to ride my bicycle to work. I am a very lucky person, but I know people who have to commute to big cities, and it's a terrible thing to do, but suppose that you had to commute to a big city, okay? What do you get? You get some level of problems, and we can ask how likely are those problems? The most likely thing that happens to a commuter in a big city, you get in the car and you get stuck in traffic. You turn on the radio and it's boring. The best possible thing that could happen to a commuter in a big city is that there is no traffic and the radio is interesting. You may get huge amounts of traffic while they're testing some emergency broadcasting system. But there is a slight chance that a commuter in a big city will be stuck behind traffic when they are run over by a drunk driver and killed. The possibilities for a driver are mostly on the bad side. And we know that, and so what do? We buy a car that has airbags, it has crumple zones, it has seat belts, it has child seats. We take out insurance. We support police who try to arrest drunk drivers. We support groups that try to block drunk driving. We pay traffic engineers to make the roads safer. We spend a lot of our transportation budget on reducing the risk of something that's not very likely because it's so catastrophic if it happens. Now, you know where I'm going with the analogy. You take the best estimate of what we face in a warming world, and the best economics says that we should be responding to that if we wish to be better off. The most likely outcome, reducing fossil fuel emissions in a wise way, makes us wealthier. It helps the economy. And because this is science, it is possible that we have overestimated what's going to happen, and so the changes are slower and smaller. We should do less about climate change. But this most likely estimate is slow, small, and expected. We might dump an ice sheet. We might lose the Amazon rainforest. We might make it too hot to live in the tropics. We might cause a lot of bad things. And most of the uncertainty is on the bad side. Now, we spend a lot of money to head off drunk drivers. And the question might be, what are we spending to head off drunk climate? I have spent a lot of my life as a communicator, and I've had the opportunity to communicate with the high policy members. And I have to tell you with absolute confidence, I have spent a fair amount of my life having this argument. Here's the most likely outcome. Couldn't it be better? This is what's most likely. Couldn't it be better? This is what we expect. See, we've now heard both sides. Let me tell you very clearly that if you wanted to hear both sides, first of all, you do not have a scientist arguing with anyone. Science is the best we have. But yes, it could be better, but there's more likelihood of making it worse. So sea level rise is almost unavoidable with warming. The published numbers have been a little low. The economists usually say don't worry much, but whether we'll respond efficiently, whether the sea level rise will be slow, small, and expected are real questions. And so there's a lot of work to do here, but that distribution is probably accurate. And so I will shut up and ask you if there are any questions while I show you a pretty rainbow.
Unmuted.
Okay, Richard, this is Louise. Sorry, it took me a second to push all the buttons to get myself unmuted. We do have a couple of questions and that have been put into the chat box. One was how excuse me, how is the IPCC report used in countries other than the US?
I believe that there is a lot of really serious attention paid to it in some countries. The people who are responsible for the Thames Barrier really are talking about do we need to raise it and by how much. The people responsible for the dikes in Holland and the Netherlands really are worried about it. They clearly have difficulty with these uncertainties because we tell them that, yeah, build for this, you have high confidence you'll get it, but with some slight chance that it will be much worse than that. I suspect there are some countries that are not using it too much yet, but I think you'd find it is mosaicked across the world depending on the attention and the abilities of the individual countries.
Okay, and I think that we had a couple of questions and you may possibly have answered them, but let me pose this one. I know you talked a little bit about this. Maybe there's some others that you can mention, or maybe you feel like you've answered it. The question was answered or asked early on. Where else are there ice shelves that scientists are concerned about?
Right. So there's a few left in Greenland that we're interested in, mostly in the northern part, northeast and northwest. And then there are a lot around Antarctica, and especially the Wilkes Basin in East Antarctica, the Ross, the Filchner-Ronne, and the ones in Pine Island Bay in West Antarctica, but also a lot of little ones, the Gets off of Mary Bird Land, and many little ones around East Antarctica, because while they all have smaller drainages taken together, they're another few meters of sea level. And East Antarctica is so big that even a little bit of it is a few meters. And you start looking at a few meters from Greenland, a few meters from West Antarctica, a few meters from the Wilkes, and a few more around the rest of East Antarctica. And that's a lot of meters. And so there's a real concern there.
Okay, thanks. And this one I think you touched on too. It's actually a whole bunch of questions in one, but I'll see what I can do with this one. It says, isn't it so that some regions melt and some stay unaltered or even growing in ice? The growing regions have a comparatively high precipitation rate, so that the melting is a picture of the plus and minus balance of precipitation versus melting edges at the swimming tongues of the glaciers. Which regions grow, which vanish?
Right. So excellent question. In the 2001 IPCC report, they said mountain glaciers will melt. Um, Ocean water will expand, but we don't think that the spreading of the ice sheets in Greenland and Antarctica will go much faster. Warming will cause more snowfall in Antarctica, and that will exceed the extra melting in Greenland. And so we expect the ice sheets to grow for the next 100 years. In the 2007 IPCC, the ice sheets had begun shrinking because the flow changed because of the flying buttresses. And so in 2001, we said snowfall beats melting, flow doesn't change. In 2007, we said, oh no, we goofed. The ice sheets are not shrinking rapidly, but they're shrinking 100 years before we expected them to. And so, in fact, in 2007, we said, here is what we expect from the extra snowfall, from the extra melting, from the mountain glaciers. Add them all together, and they give you this much sea level rise. And we don't know what the flow will do. So you take a guess and add it to the other ones. And so the 2007 doesn't actually have a prediction because we couldn't do the ice dynamics. So the extra snowfall is mostly in the middle in the cold places. And there's a big cold middle of Antarctica and a smaller cold middle of Greenland, and we expect them to get more snowfall because warmer air carries more water. But the concern is now that the flow changed much faster than we expected.
Okay, great. One question that I'd like to throw at you about science communication. We really appreciate you focusing on analogies in your presentation tonight and kind of talking to us about thinking about those. And one person has asked, how do you come up with your analogies?
Oh boy.
Have any help for
Um,
us there?
yeah, well, I get to teach. And I think probably the same as almost all of you. I talk to people and you try something and it doesn't work. And you look at them and you say, boy, that's a blank stare. And then you try something else and you try something else until it works. My secret, in addition, is I have that bicycle. And I can think about things while I'm riding to and from work, and and the phone doesn't ring, so, but I'm not sure exactly where they come from. But very clearly, teaching is hugely important for this, and working things with students and talking to people. Certainly for your students, um, when they say, well, I tried to write a good term paper and it didn't work, you say, did you read it to yourself? Did you read it to your hamster? Did you read it to your neighbor or your mother? Because the moment you read it, you'll realize how stupid the stupid parts are.
Okay. Well, great. We may have a couple of questions, a little bit of time at the end to ask you some more questions, but I want to be sure to leave plenty of time for Nell. So I'm going to thank you right now and put you on hold, Richard, and I'm going
Great.
to unmute Nell.
Thank you all.
Okay, and I'm going to mute you, Richard. Thanks again. Nell, are you there?
I'm here.
Great. All right, I'm going to be switching the screen over to you now.
Okay.
Nell, you seem to be signed on twice, so maybe I've given you
Oh,
to
I've
one.
gotcha.
Do you have it? Because I'm not seeing you up. Are you?
There I am.
There you are. Okay.
Yep.
Whoops. I've lost you again. Hang on. Sorry, everybody. There you are. Okay.
All right.
All right. So it's my pleasure to introduce our next speaker, which is Miss Nell Herman. Nell's a middle school science teacher in Blue Hill, Maine. She holds a master's degree in ecology and conservation biology, as well as in wildlife and fishery science. She's worked on several field research teams, taking her to Venezuela, Costa Rica, Greenland, and Antarctica. Nell uses many techniques and best practices to transfer science research to her students. So welcome, Nell.
Thanks. It's great to be here. So before I get rolling with the lesson plans that I'm going to share, I want to talk just a little bit about how, as a classroom teacher, I found my way to Polar Educators International, because that's something that I get asked sometimes. It's a somewhat unusual path, maybe, but one that I definitely like to share with other teachers who are listening, because it's opened a lot of doors for me, and more importantly, it's opened a lot of great doors and opportunities for the students that I'm fortunate enough to work with every day. So I've been teaching science at the middle school and high school levels for 14 years now, and like Louise said, right now I'm teaching in coastal Maine. You can see where I'm located on the map there. Before I moved here, I was teaching in State College, Pennsylvania, which is the town where Penn State is located, and that's how I actually met Richard. So I first met Richard in 2010 when some students who I'd been working with won a video competition that was being sponsored by Penn State. And so the kids had developed a music video about deforestation, and Richard actually came to the award ceremony to present them with a check, which they used to buy materials to build a living wall in our school. And so naturally, he arrived with his guitar in hand and proceeded to engage the kids with a great song and his sense of humor and his amazing ability to make science accessible and fun, which is something that's always been a goal of mine. So since that time, he's been a role model for me and a real hero. And so that's how that connection initially was established. But I'm sure it's no surprise to people who are listening that my greatest successes as a science teacher have happened when I've involved kids in real world science. And I've also had some great success in using older students to teach younger ones about various topics in science. And I've used this model many, many times, but have been most pleased when I used it recently with a student group I developed at State College Area High School called the Polar Ambassadors. And I'll talk a little bit more about them. I did work in State College for 11 years and just this year moved up to Maine. So I'm teaching now. There's a little nod to State College. And this is the school where I'm teaching now in Blue Hill. So I work in a K through 8 school. We have only 250 students. Just to give you some context, it's a public school, and 37% of the students receive free and reduced lunch. I'm the only science teacher for kids in grades 7 and 8. We live right on the ocean, so we're surrounded by natural beauty, and it's been exciting for me this year to bring my fascination with the Earth's polar regions here to coastal Maine. So I'm working on getting a group of polar ambassadors started here in Blue Hill also. So this is just a little history about kind of my path, I guess, to the polar regions. And it started in 2009 when I was teaching 7th grade science in State College, Pennsylvania. And the parents of one of my students are researchers at Penn State who study the effects of climate change on caribou. So Eric Post and Pernilla Booving, who are actually the people who spearhead the Polar Center at Penn State University, do their field work outside of Kangerlussuaq, Greenland. And they very graciously invited me to help them with their field work and to share what I learned with my students in State College in the spring of 2009. So this experience really changed my life. And while I was in Kangerlussuaq, I just absolutely fell in love with the tundra and the science that surrounded me at KISS, which is pictured up there in the upper left-hand corner. It's the Kangerlussuaq International Science Station. So I was really excited to participate in field work and share that experience with my students, and also very thrilled to have a chance to interact with scientists who do research in the Arctic. So I met all sorts of amazing folks, including people who are associated with the NEEM Deep Ice Coring Project. So after that experience ended, I really couldn't stop thinking about it. And so I kept pestering Eric Post to try to get me back to Kangerlussuaq, and he actually found something a little different and equally exciting. So he had been visiting the Office of Polar Programs at NSF and came across a brochure for Polar Trek, which is an acronym for Teachers and Researchers Exploring and Collaborating. And it's an opportunity for American teachers that's funded by the National Science Foundation and coordinated by ARCUS, the Arctic Consortium of the United States, which is based in Fairbanks. So I applied for the program, never thinking I'd be selected, and was just thrilled when I was offered an opportunity to work with marine biologists from the University of Alabama at Birmingham. And these are just amazing people, Chuck and Maggie Amsler and Jim McClintock, who were doing a project about ocean acidification on the Western Antarctic Peninsula. So for my Polar Trek experience, I spent 5 weeks at Palmer Station and again was immersed in polar science and surrounded by just some of the most amazing people who were very willing to explain what they were doing, very willing to Skype with my students, very willing to help me share this information with kids in any way that they could. So I was able, while I was at Palmer Station, to share my experience with my students at home through the Polar Trek website, where I kept daily photo journals, and also through Skype and other webinar types of events with kids in my school and also kids really all over the world. So that was very exciting. And then from there, it continued in the 2012-2013 academic year. I got hooked up with a research experience for teachers that was through the Palmer Long-Term Ecological Research Project, or LTER. And through that, I worked with Beth Simmons, who's the education and outreach coordinator there. And we developed some lesson plans about autonomous underwater vehicles and remotely operated vehicles and the technology behind those and kind of how and why marine scientists and polar scientists use them. So through all of these opportunities, I was able to make these really amazing connections, including to PEI, which is just a tremendous committed group of people. So I would encourage anybody who's listening to get actively involved with PEI, whether you're a teacher or a researcher, because the opportunities are just phenomenal. And similarly with the Polar Center at Penn State, that's been a really great way for me to network as an educator with researchers and learn from them. So before I left for Palmer Station in 2012, I developed a group of about 20 high school students. They were boys and girls in grades 9 through 12, and we called ourselves the Polar Ambassadors. So the group was an extracurricular activity, and we met weekly after school to talk about polar science. So we were very fortunate because we're located near Penn State University, so we had really easy access to researchers who do work in the Arctic and the Antarctic. And many of these people very generously visited my classroom to talk to the students about their research. I also spent time with these kids developing and testing lesson plans about polar science, and we mostly tested these with younger students. So we did outreach to over 800 kids in elementary and middle schools in our own school district and in surrounding districts there in central Pennsylvania. And we took part in some local sustainability festivals and other local science fairs and outreach types of events. And I found that when I gave these kids an opportunity to be the experts, that they just blew me away. They flourished. They developed a huge sense of pride in what they were doing, a huge sense of pride in the message that they were sharing. And there were times when their understanding of polar science floored me. They knew things I didn't know that they knew. They, read articles in the New York Times and in other places and would talk about them. So it was really just a fabulous, fabulous group of kids and a great opportunity. And just recently, actually, I went home to State College for the Polar Day at Penn State event, which is sponsored by the Polar Center there, and was really excited to hear from a former polar ambassador who's actually going to spend 8 weeks this summer in Kangerlussuaq, Greenland, working for a grad student as his field assistant. So that was pretty exciting for me to hear. So when I moved away from State College just this year, I decided I really wanted to continue with the Polar Ambassadors idea. And so this is my first year in my current job, but I've managed to incorporate polar science into the curriculum. And so I bring it to my classroom anytime I can. If there's a logical connection to a topic I'm teaching in class, I try to make it. Sometimes we do things just for fun, like eat cake on Antarctica Day to celebrate the signing of the Antarctic Treaty. And I've had some visitors come in and share things with students, including Buzz Scott, who's an ROV pilot who worked for the United States Antarctic Program. That's him in the upper left-hand corner photo, teaching kids how to operate an ROV. And he brought survival suits to school and talked to kids about, surviving in Antarctica and these types of things, which got kids very engaged and very interested. And then in the bottom right-hand photo is a researcher from the University of New Brunswick, Gustavo Chang, who visited my classroom and talked to kids about his research on leopard seals in Antarctica. So all of these things definitely, capture the kids' imagination and get them interested in these parts of the world and the science that's happening there. So the lesson plans that I will talk about today relate nicely to Dr. Alley's talk. I wish I had known about the traffic jam and flying buttresses analogies before I taught these to the kids, because those are great. But these are ones that I've used with my 7th and 8th grade students this year in Blue Hill, Maine. I think they could be easily adapted for high school students too. They're engaging. And as a person who has taught both middle school and high school, I think they would appeal to both age groups and also to students of varying ability levels. All 3 are modeling activities that involve simple, inexpensive materials. And as I said before, the kids found these lessons really engaging, but particularly the one called "What If the Ice Shelves Melted?" And I think you'll see why. All of the lessons come from the ANDRIL, the Antarctic Geological Drilling Education Program, and all of the activities can be found online at the website that I've got listed there. So they're from the Antarctica's Climate Secrets and Flexibit curriculum, specifically from Units 2 and 5. So let's see, the 3 activities that I'm going to talk about today, one is from Unit 2, which is about Antarctica's ice on the move, and the other one is from Unit 5, Decoding Antarctica's Climate History. So I'll just go through each of these activities sort of step by step to give you an idea of what they entail. Each of the units includes a banner that has these incredible graphics and images, and these are all online in both PDF and JPEG formats. The other great thing to know is that they're available right now in English, New Zealand English, Spanish, Italian, German, and French, and they're currently being translated into Portuguese. So just to give you an idea, this is the banner for Unit 2, Antarctica's Ice on the Move. The website also includes a number of really great podcasts and videos. And this is the banner from Unit 5, which is Decoding Antarctica's Climate History. So each unit includes detailed lesson plans which address climate science topics in the next generation science standards. And I realize we've got an international audience right now, so the standards I have listed here won't be relevant to our entire audience of educators, but I'd actually be really interested to learn more about science standards in other countries. It's not something with which I'm at all familiar. So maybe in a discussion thread after tonight or at some point that topic could be a brief conversation, because I know for one I'd like to learn more about that for sure. But at any rate, the middle school standard addressed by these lessons is listed here, and it involves kids asking questions to clarify evidence of factors that have caused climate change since about the beginning of the Industrial Revolution. And the high school standard involves using models to address changes in climate also. So with the kids, before I really dove into these lessons, I did a bit of background information and review. So forgive me if this is all a little bit elementary, but my typical audience is 13-year-old kids, and I figure review never hurts. So here's a basic map of Antarctica. So this is one I shared with my students that came from the ANDRIL education website. And so I point out that the West Antarctic ice sheet includes the Western Antarctic Peninsula, which is where I was for my polar trek experience. I point out the fact that it's smaller than the East Antarctic ice sheet. I point out the fact that the 2 ice sheets are separated by the Transantarctic Mountains. We talk about the idea that there are many ice shelves in Antarctica, but the lessons that I'm going to talk about tonight focus specifically on the ice shelves here, the Filchner-Ronne Ice Shelf, the Ross Ice Shelf, and the Emery Ice Shelf in East Antarctica. And then we do a little bit of review of some kind of basic ice vocabulary. So starting with glaciers, that's actually me floating in the Southern Ocean to test out a survival suit, which worked, fortunately. But, you know, we remember the concept that glaciers are made up of fallen snow that's compressed into large, thickened ice masses over many years. And then we move on to our conversation about ice sheets, which are areas where the glaciers have grown so large that they've merged together to cover big areas of land. And we talk again about the East and West Antarctic ice sheet and the fact that there's an ice sheet that covers much of Greenland. We talk about ice shelves and the idea that over time ice flows downhill, and that when parts of an ice sheet flow off the continent and float on the ocean water, that's when you end up with an ice shelf. Then we talk a little bit about icebergs. So at the leading edge of an ice shelf, we know sometimes that sections of ice break off, and it's those free-floating chunks that are icebergs. And then we kind of finish this vocabulary conversation with sea ice, which is really different from the other types of ice because it's frozen seawater on the ocean surface. And so we talk about the idea that each winter the area covered by sea ice around Antarctica expands, and then by summer much of it melts away again, leaving open ocean in its place. So I will start with this activity, 5B, mostly because of the 3 lesson plans I'm going to talk about. This one was probably the most well received by students, and I think you'll see why shortly. It's a modeling activity, but it's really great. So the overarching idea in this lesson is that if the ice shelves in Antarctica melt or continue to collapse and melt, the ice sheets will move off the continent at increasingly rapid rates. And so the materials needed for this one are inexpensive. I used the lesson plan with all 4 of my science classes. I tweaked it a little bit each time. I did find that it worked best if you had kids working in pairs, but you could probably have them working in groups of 3 or 4. So if you follow along on this slide, you can see the steps are really simple. First, students cut out maps of the continent, and the maps are provided in the lesson plan online. The ice shelves are sort of overlays, so I'll show you a picture here in a minute so you can see what I mean, but they're on the map itself, and then they're also separate. So the kids cut out the 3 separate ice shelves and place them on top of the map, and they're removable to show what would happen if the ice shelves did disappear or collapse. So next, the kids are going to cover the map with packaging tape. You could also laminate them in advance if you wanted to reuse them, but that would take some advanced prep work. And then the kids use foil to line the underside of the continent, and they also do the same thing with the little ice shelves. And they build up a wall around the edge that's about 1 centimeter tall to hold the ice sheets in place. Then after that, they're just going to take some modeling clay and they're going to build the transantarctic mountains to separate the West Antarctic ice sheet from the East Antarctic ice sheet. And so here's that same picture of the map again. So this is actually the handout that you give to the kids, and they cut out the continent on the solid line. They don't cut those dotted lines, but they then cut out the 3 ice shelves separately to use those as sort of like overlays that will go on top of the model. And then they'll pull those out when it's time. So I'll show you a picture of that. But the next part is the really fun part. In steps 5 and 6, the kids make this weird gloopy kind of polymer stuff out of white glue and water and borax. And they use it to cover the continent and model the ice sheets, and then to cover those little ice shelves themselves. So then what they do is they actually pull the ice shelves off the model, and the ice sheets, so the gloop on top of the East and West Antarctica regions begin to flow off the continent and onto the wax paper, which represents the Southern Ocean around Antarctica. So it takes about 10 minutes before you see a dramatic result. So at this point, I had the kids start sketching the model, which is one piece of the assessment that I used at the end of the activity. And this kind of kept them looking at the model, and it also kept them focused, which is good, especially with middle school age kids. So after about 10 minutes, it's pretty clear that if the ice shelves collapsed, that the ice sheets would ooze or melt or leak into the Southern Ocean. And it's also pretty obvious that this would happen more in West Antarctica than in East Antarctica. So to assess this with the kids, I did really a couple of things, both of which were recommended on the Andrel Education site. So I had them sketch the model before and after, as I mentioned, and I also had them write a short paragraph about what happened and how realistic they thought the model was and what differences they observed between East and West Antarctica. So the responses I got from kids about this one were great, and they talked about this activity for quite a while and actually wanted to do it again because they liked it so well. So that was a great one. The next one I will talk about is activity 2B, which is called When Ice Meets the Sea. And so the big concept here is that ice sheets move downhill over time, and when they meet ocean water, they melt, depositing debris on the ocean floor. This is also a fun one, but it takes a little bit more advanced prep the night before, because you've got to freeze some ice sheets. So in advance, you'll need to freeze water in some baking pans. So I actually use the disposable ones, but you know, they're inexpensive and you can reuse them multiple times. So you want to fill those pans with water about a centimeter deep, and then you need to sprinkle in some gravel and sand and pebbles before you put them in the freezer. So again, I did this the evening before to get ready. And I had kids work in groups of 2. That worked pretty well, but I am very lucky because I've got small classes here in Blue Hill. My largest class is 15 kids, so I don't need to purchase quite as many materials as some other teachers probably would need to. I'm sure larger groups would probably work too, as long as everybody had a role to play in the activity. So in the paint pan, then kids will make seawater using salt and blue food coloring and water. And this should be poured into the paint pan until it's about a centimeter from the top edge. I found this graphic to be really helpful for kids when they were trying to sort of visualize exactly what it was that they were modeling. So this is right on the website, and it really kind of helped clarify things for the kids. Next, you can take a piece of copier paper and cut it in half and add that to your model ocean to represent the sea ice. So that's pictured there in step 3. And then you want to point out again to the kids that the slope of the paint pan is what's representing the land. And then what they will do is they'll take the ice sheet and they'll place it sediment side down on the slope of the pan. So that's the land part again. And they're going to be pushing it slowly downhill to model the downhill movement of the ice sheet. So I had them move it about 1 centimeter per minute, and that was good. I found that the kids could get a little squirrely and unfocused at this point. So during this part of the activity, I kind of had them review vocabulary about ice sheets, ice shelves, sea ice, icebergs, and so on. And we talked about what we were doing, you know, and the fact that as the ice sheet is moving into the model ocean, it's becoming an ice shelf. So that was all very good. Then once the ice shelf has melted a little bit, it's easy to see the rocks and gravel and sand that have been deposited on the sea floor. So that is a very good visual for the kids. So the Andrel website offered a couple of suggestions for assessment. In this case, I used the second one. It would be a good model to recreate and explain to younger students or another audience if you had time to do that. I didn't have time, so instead I had my students draw diagrams that included ice sheets, ice shelves, and icebergs, and sea ice, and I had them label it. So they ended up looking something like this. And that was successful. That worked out well. And then the last activity that I'll talk about tonight is activity 5C, which is called How Does Melting Ice Affect Sea Level? And this one is a little bit more simplistic than the other 2, but it also worked well, I thought. The overarching idea with this one is that when ice that's already floating in the ocean melts, sea level doesn't change. So this includes all floating ice. But when ice that's on land runs into the sea, so glaciers and ice sheets, additional water is being added to the ocean. So in this case, sea level does rise. So again, it's simple materials for this one. We just used a couple containers, one to model ice on land and the other one to model ice in the water. So you add gravel to each container in a way that it slopes and is piled up at one end to form the land. And then you add water to each container to represent the ocean, but you have to make sure that that water doesn't cover the gravel. So you want the land to stay dry. And then you will add equal amounts of ice to each container. Actually, I should go back here. In the ice on land container, you're going to put the ice on top of the gravel. And in the ice in water container, you're adding the ice to the water. So once you've done that, you need to mark the water level on the outside of each container, and then students just have to wait for a little while for the ice to melt. And after that's happened, the water levels need to be checked and marked again. And what you'll see is the water level rises in the ice on land container, but not in the ice in water container. So that's also a good visual way for kids to understand this concept. And so finally, for this one, to assess kids, I simply led a class discussion about the changes in the water levels because this was kind of just a quick and easy one. But you could always use an extra set of models to demonstrate the big idea to a different audience. So that was a good suggestion on the website. So that's actually all I've got. That's the end, if you will, of a Gen 2 penguin. But as I mentioned, this curriculum is really great. I'd like to use more of it with my students. So far, I've only used the 3 lesson plans that I talked about. I would definitely love to hear from folks, so don't hesitate to ask questions or share ideas tonight or after the fact. I always like to share ideas and excitement about polar science for sure. So thanks very much for being here tonight.
Thanks so much, Nell. That was great. And your pictures really showed exactly what to do. That was really, really nice and very clear. We had a couple of questions. Which of these concepts did you find that the students had the most trouble with, if any?
Um, they really seem to understand things pretty clearly and pretty well. I don't think they really struggled with any of the concepts, but maybe if any, that last activity that I talked about, we talked about if you have a full glass of water with ice in it and the ice melts, does the glass of water overflow? And I don't know why, but in my 14 years of teaching, that's always been kind of a hard concept for kids to grasp. So maybe that one. But overall, I think, each of these lesson plans is so hands-on and so visual that it's really pretty easy for kids to get these ideas.
Great, thank you so much. Um, we are quickly coming to the end of the scheduled session. Um, what I'd like to do just real quickly is share my screen again. And so hang on one second. There we go. Sorry, had a little trouble getting my screen up. And just real quickly, if my organizers, are you seeing my screen this time and my slides? I
Yep.
understand. Okay. I understand there was a little trouble on the slides before. So um, let me just bring this up real quickly here. Since I didn't have my slides before, I just wanted to show you what Dr. Alley looked like and Ms. Herman. And before we end our webinar tonight, just wanted to go through a couple of things real quickly. Nell had showed you where these activities can be found, so I wanted to put that link up again, the URL for those. And that the banners, there are 5 banners, and like she said, they're available in 6 different languages. And then real quickly, some masterclass reminders. Thank you so much for being here tonight and participating. There will be a discussion forum that you can begin to sign into. So a lot of you are already signed into it. We'd like for you to be ready to officially begin on Monday. We want to give people that were in inconvenient time zones tonight the chance to be able to see the archive, which will be online tomorrow. To earn a certificate of participation from PEI, you need to take part in the live webinar like you did tonight, or others can take part in the archived one. I'd like for you to introduce yourself in the discussion forum and take part in discussions regularly over this next 2-week period. commenting on other people's comments or adding in your own threads. Also, write a one-page reflection on this webinar tonight. We'd really like to hear your thoughts about what you learned about science communication, and also the hands-on demonstrations. And then there's a pre and post survey available within that discussion forum. We plan to do future master classes, and those times, dates, and presenters are being finalized right now and will be announced soon. We're hoping to do this summer in the New Zealand time zone, and in fall we'll probably be back in a US time zone, spring in Portugal. So hopefully some of those time zones will be more convenient for people that weren't able to be here tonight. So again, I want to thank you for taking part tonight in our PEI Masterclass series, and a lot of work went into planning and organizing this, and I just wanted to get everybody's name up here that were involved in the background of what was happening here tonight. And I did not see questions, any other questions, but what we'd like for you to do is add questions to the discussion thread. And Richard, I'm unmuting you right now, and Nell, you are unmuted also. Thank you so much for being here, both of you, for all of the time you put into getting ready for tonight and for your presentations tonight. So thank you for being here.
Well, thank you. A real pleasure.
Same.
All right. And we will sign off. Again, if you have any questions or comments about Masterclass, please go to the website, polareducator.org, and sign into the members area and take part in those discussions. Thank you, everybody. Good night.
Good night.
Thanks. Bye.